solid uniform sphere of mass rests on a perfectly smooth ramp that is inclined 35 degrees above the horizontal. The sphere is kept from rolling or sliding down by a horizontal wire that is attached so its point directly towards the sphere's center. So draw a free body diagram showing all forces acting on the sphere.
We have a problem here where it's horizontal wire that is holding a solid uniform ball and a wrap that has a 35 degrees angle relative to the horizontal surface of the ramp. It's perfectly smooth, so we don't have to worry about the friction, and the wire is directed away from the center of the ball. To draw a free body diagram for the ball is first you need to set up the coordinate system. The X and Y are at a slant. So we only have three acting forces on the ball. One of them is the weight. It will go down. So we will label this W for the weight. And the normal force is perpendicular to the surface of the ramp. So here it is. And we'll label it N. And lastly is the tension of the wire. The tension of the wire, the picture points directly to the right, so it goes to the right. Tension appears to be at an angle relative to the x-axis in this coordinate system, and the weight appears to be at an angle relative to the y-axis. They're actually the angle as the one that we are given, the 35 degrees. So the theta is equal to 35 degrees, which is in here 35 degrees. So that is our free bodies diagram.
Now let's find the magnitude of a normal force. So let's take forces perpendicular to the ramp. So in that direction, nothing moves. So the net force is 0. That means n minus weight cos theta minus tension sine theta is equal to 0. When we arrange this equation, it now will become n equals weight cos theta plus tension sine theta. So we already know from the parallel to ramp direction that tension cos theta minus weight sine theta is equal to 0. So before that, we all tension is equal to weight tan theta, so y. So let's derive this. So tension cos theta minus um, weight sine theta is equal to 0 because the gravity has a downslope component, weight sine theta, and the horizontal tension also has a component up the slope, so tension cos theta. Because t is horizontal, the angle between t and the parallel direction is 90 degrees to theta, so the parallel component is t cos theta. So to solve for t, let's say phi cos theta is equal to weight sine theta. So t is equal to weight sine theta over cos theta. So we all know that sine theta over cos theta is tan theta. So that's why our t is equal to weight tan theta. So let's plug this tension to our equation. So this is our equation, right? This is our equation. So we already have the t. That's why it's t. Like yeah. So n is equal to weight cos theta plus our t tension, weight tan theta times sine theta. So n is equal to weight times cos theta plus sine squared over cos sine squared theta over cos theta, and n is equal to mg over cos theta, so y. So let us simplify this through the Pythagorean theorem. So here n is equal to mg cos theta plus mg sine squared theta over cos theta. So n is equal to mg cos squared theta over cos squared theta plus mg sine squared theta over cos squared theta. So like n minus n is equal to wait cos theta cos squared theta plus sine squared theta over cos squared theta. And we all know that cos squared theta plus sine squared theta is equivalent to 1 according to the Pythagorean identity. So that's why mg times 1, it will now become mg. So n is equal to mg for weight over cos theta. And since our theta is equivalent to 35 degrees, so n is equal to weight over cos 35 degrees. So cos 35 degrees is equal to 1.220.
We have a solid uniform sphere resting on a smooth ramp inclined at 35 degrees. The sphere is not sliding or rolling because it's being held by a horizontal line. Now, we are asked to find the tension in that wire. We will now solve for the tension and apply Newton's second law. Tension is horizontal, not along the ramp. But since the ramp is inclined at 35 degrees, the tension component along the ramp is T cosine theta, and the component of weight along the ramp downward is W sine theta. So, the full equation along the ramp is the summation of f sub x is just equal to t cosine theta minus w sine theta equals 0. Why is it equal to 0? It is equal to 0 because there is no acceleration or the sphere is not moving. Now we are going to solve for t cosine theta. Since it's just equal to 0, we can easily conclude that t cosine theta is just equal to w sine theta. And in order for us to get t, or tension is, we are going to divide both sides by cosine theta. Now cosine theta is cancelled, and we all know that sine theta over cosine theta is just equal to tan or tangent. So the answer is W tan theta. And also it is stated that the angle is 35 degrees. So the answer is W tan 35 degrees. Or if we are going to calculate it, it would be just equal to 0.7 times W.
So here is the second problems for Newton's law. A rocket with a total mass of 125 kg is equipped with an engine that delivers a constant upward thrust of 1720 Newton. Inside the rocket, a small electrical power unit weighing 15.5 Newton is placed on the floor. So here's the first question. Determine the rocket's upward acceleration given this thrust. So so for the first step, we must determine the rocket's weight. So to solve that, we have the formula weight equals m times g. So the value of mass equals 125 times with the gravity 9.8 equals 1225 newtons downward. Next is to find the rocket's net force. So to, f- to solve the net force of the rockets, we have the formula F net equals thrust minus weight. So we have the value of thrust 1720 newtons minus the weight that we already solved in the first step is 1225 newton. So it's equal to 495 newtons upward. So for the third step is the acceleration. We must find the acceleration. So to solve that, we have the formula F equals ma, where m is the mass and a is the acceleration. Then so we before that we must derive the this formula to find the acceleration. So we must find the acceleration. So F equals ma. So to derive that, we divide the m then. So it will equal to a equals f net over m. So that's why we come up with this formula. So this is already the derivation of acceleration formula. So we must substitute the given. So the net F net equals 495. So the newtons is is just the same with kilogram times m over a squared. Then the value of m equals 125 kilogram. So so equals 3.96. So we must apply the cancellation, cancel the kilogram, then ang nabili na lang is meter per second squared. That's why we come up this answer. 3.96 meter per second squared upward. Okay, that's all.
So good day, sir. The given problem is a rocket with a total mass of 125 kilogram, including all its content, is equipped with an angle engine that delivers a constant upward thrust of 1,720 Newton. Inside the rocket, a small electric power unit weighing 15.5 Newton is placed on the floor. When the rocket has ascended to an altitude of 120 meters, calculate the force exerted by the floor on the power unit. So first we need to find the acceleration of the rocket. So the acceleration of the rocket is 3.96 meters per second squared. Since the final answer of squares to be polygon, so I don't need to explain it further. Kay nananik first B. So second one is to analyze the force acting on the power unit. So this is the formula we use. No, F floor minus weight of the power unit is equal to mass of the power unit times acceleration. So in this video or in this explanation, we need to find the F floor. So we have already weight of the power unit which is 15.5, and we don't have yet mass per unit, so we need to calculate this first, or we need to find this first, and we'll have already acceleration. So to get the mass per unit, so we need to divide the weight of the power unit divided by the gravity. So 15.5 Newton divided by 9.8 meter per second squared is 1.58 kilogram, approximately, only since two decimal places we use this in this. So we have already weight of the power unit, mass of the power unit, and acceleration. So we need to plug the value on the equation. So F floor minus 15.5 Newton. So 15.5 Newton is already given, and it is the weight of the power unit is equal to 1.58 kilogram. The answer of the mass per unit power unit, so times the 3.96 meter per second, which is the acceleration of the rocket. So first we need to multiply this. So 1.58 kilogram times 3.96 meter per second, 3.96 meter per second squared is 6.26 Newton. So And the second one is we need to transpose the negative 15.5 or the weight of the weight of the power unit in the other side. So transpose it. So now we have 6.26 newton plus 15.5 newtons. So we have 21.76 newton. So the exerted floor of the rocket is 21.76 newton.